Great. Thanks for having me. Hope everyone can hear me okay and see the slides okay. Um, I'm going to give a reprise of a talk I gave at AAAI a couple of days ago, the theme of which is no AGI, and for that matter, no trustworthy AI without neurosymbolic AI. And, the general question is, how do you get to AGI? Or a lesser goal is simply trustworthy AI. So I'll give a definition of what I mean by AGI, artificial general intelligence, in a minute. But if you think that's too ambitious, you can set a lesser goal. How do we get to AI that we can trust, that doesn't hallucinate all the time, isn't unreliable, that you can actually use it with the same confidence that you might use a calculator? So first, on the topic of what is AGI, there are a lot of definitions floating around. I gave my own when I offered Elon Musk a $100,000 bet that he never took. And he claimed that we would see AGI by 2029. I said, let's define our terms. And I said that I took AGI to be a shorthand for any intelligence that's flexible in general, with the resourcefulness and reliability comparable to or beyond human intelligence. And I actually checked that definition with Shane Legg and Ben Goertzel, who are the people who originally coined the term, and they were cool with it. So that's at least one way to take what I might mean by AGI, is having that resourcefulness and reliability that we would expect from humans, or maybe even beyond humans. And then on the right, I had some examples of kind of ways you might operationalize that. So for example, solving a comprehension challenge where you could watch a video and answer arbitrary questions about it, etc. So if you want, you can read that at my Substack, GaryMarcus.substack.com. It's, I guess, from about a year ago. All right. One hypothesis is so popular that somebody made a t-shirt of it. And that hypothesis is the idea that scale is all you need to get to artificial general intelligence, or maybe even just reliable intelligence. And it was based in part, I guess, on a early finding by OpenAI that certain things scaled. And what I've always said to this is that these are not physical laws. They're not like gravity. These are laws that are really just empirical generalizations, and they might hold for a while, but that doesn't mean that they'll always hold. So I think the operative thesis behind a large part of the whole field of AI in the last several years is that if you just add more data, more compute, that whatever problems we see now will go away. And I've been skeptical of that for a long time, but it's certainly a prominent idea. The general theme that people have been running with for the last several years was kind of articulated in a way by a large group of researchers at Stanford in August of 2021 in their paper on foundation models, which introduced that term. The notion behind a foundation model is you train some very big neural network on a whole lot of data, and then you adapt it to particular tasks. As soon as it came out, Ernie Davis and I wrote a reply in the gradient asking, has AI found a new foundation? And what we pointed out is that the thing you most want from a foundation is reliability, is soundness. You don't want to build a building, a house, or a skyscraper on a foundation that's weak and unreliable. And we argued that foundation models were in fact weak and unreliable. And then in March of 2022, I wrote a paper that I think enraged a large part of the machine learning community called Deep Learning is Hitting a Wall. And the argument I made there fundamentally was that scaling was not going to get us all the way to artificial general intelligence. And that infuriated a lot of prominent people like Sam Altman, who parodied, if you compare his graphics and mine, is obviously parodying me. And he said, give me the confidence of a mediocre deep learning skeptic. And Yasha Bach had a hilarious cartoon with a robot leaping far over walls. Greg Brockman had a cartoon that I still think is funny 2 years later, but not for the reason he intended it. He tried to get DALL-E to say deep learning is hitting a wall, and DALL-E actually came back with deep leapening. And I think that that's been kind of characteristic, in fact, of a problem that has not gone away, which is that these systems have trouble simply even repeating text. Jan LeCun, in his characteristic bombastic style, said, and I should say this is the earlier Jan LeCun, there's a more recent version we'll talk about later, but the earlier Jan LeCun of 2022, before uh, ChatGPT ate his lunch, was prone to saying things like this: not only is AI not hitting a wall, but cars with AI powered driving assistants aren't hitting walls or anything else either. I think a lot of what he said there isn't really true, and I don't think even he believes it anymore. But that's where we were in 2022 in the spring. It was a lot of confidence around the scaling hypothesis and a lot of anger expressed that there might be any problems with it. Nando De Freitas, who's an executive at DeepMind, high-level executive there, wrote his opinion is it's all about scale now. What's over, he means that the AGI game is over. It's just about making these models bigger, safer, compute efficient, faster at sampling, more memory, more modalities, etc. Well, we now have more modalities. We certainly have more data and so forth. I don't think we're anywhere near solving AGI. So just change so I can see a little better. By now, I think the scaling hypothesis has been funded orders of magnitude more than any other hypothesis in AI history. So, it's been funded billions of dollars. Nothing else has ever been funded like that. And an optimistic case would be that it's made immense progress, and it wouldn't be untrue. We have ChatGPT, we have GPT-4, Gemini Pro, Sora, Codex. None of those things existed when I wrote my critique in 2022. All of them have found some utility. But I would say that if you're objective about it, you'd also have to acknowledge that it has failed to yield AGI, that what we have right now is not as reliable and resourceful as a human being. It has failed to replace radiologists, as Jeff Hinton once promised in 2016 would happen roughly by, well, even a few years before now. It has failed to solve autonomous driving. Some of these real world tasks where you need genuine autonomy, it's really not up to it. I would say it has failed to solve common sense. It's failed to provide a reliable and trustworthy basis for AI. We've seen a million demos in the last couple of years of what systems like ChatGPT can do, but most of them are demos. They're not things that you would just trust to run on their own. They require humans in the loop. They work some of the time, not all of the time. I would say we've also failed to solve the long-standing bias issues. We could talk about what happened with that last week a little bit later. And interestingly, I'm no longer alone. Tech leaders themselves are starting to back away from scaling is all you need. And I have a few samples. One is from Sam Altman on the left, who mocked me as a mediocre deep learning skeptic and now says, well, we need another breakthrough. We can push on large language models quite a lot. We'll keep doing that. But within reason, I don't think that doing that's going to get us to AGI, blah, blah, blah. So Altman has started to sound a little bit like me, if you read carefully what he's been saying lately. Bill Gates said that he thinks that GPT-5 is not going to be a lot better than GPT-4, that we might be reaching a plateau. He said that in the fall. Jan LeCun had a transformation after ChatGPT beat out Galactica. Now he sounds like me. Somebody ran a poll, and the winner of the poll was what explains Jan LeCun's recent tweets. And the answer was ChatGPT trained on @GaryMarcus tweets. So here's a pretty good example of that. On the highway towards human level AI, large language model is an off ramp. That's more or less a paraphrase of saying deep learning is hitting a wall. And then Demis Hassabis just a few days ago kind of changed his view. Last summer, he was saying maybe scaling will get us all the way there and maybe not. And last week he said scale is only going to get you so far. So I think it's significant that these tech leaders have actually changed their tune. So I made a joke the other day that we'd be selling T-shirts in the back. Scale is all you need with a red circle around it. I don't think it's a viable hypothesis anymore. Something that I've been saying for a long time, since 2012, is deep learning is a better ladder, but a better ladder doesn't necessarily get you to the moon. So the question is, what might get us to the moon? I don't have a full answer, but I have at least a little bit of a sketch. So if not scale, then what? Well, the first thing I would say is, it's not that we need to get rid of deep learning and large language models, which are, of course, a form of deep learning, altogether. A lot of people read me as saying, well, we should just go back to symbolic AI. And that has never been my claim. For about 30 some years, I've been arguing that we need hybrid models that include both some elements of classic AI, including ontologies for sure, and also some elements of neural networks. And so an easy way to strawman me is to say that I think that we just need symbolic AI. That's not my claim. Um, in fact, I think for certain areas of perception, for example, deep learning is far better than anything I can imagine coming out of symbolic AI. But there are other things like planning where I don't see how deep learning is ever going to be an adequate solution. You might know some of Rao's recent work showing how bad deep learning or large language models are at that. I think that we have to understand from a cognitive science perspective that many different things go into human cognition anyway. And we don't want our AI to be exactly like human cognition, but we should certainly take clues from human cognition because it is the only flexible general purpose system that we really have so far. And if you look at human cognition, you have things like perception, language, reasoning, analogy, planning, common sense. Deep learning has made real progress on perception, some progress on language, but I think it's deeply problematic. I think it's actually made very little progress on reasoning, not so much on analogy, though not none, almost none on planning, and not so much on common sense, though you can make some arguments about it. Oops. So in an article a few years ago called who was called The Next Decade in AI, I proposed a 4-part plan. And the first part plan was a focus on neurosymbolic AI. And that's something that I've been advocating for since my 2001 book, The Algebraic Mind. Well, what is neurosymbolic AI? I think the first question is, what do you mean even by symbolic AI? And a lot of people have written about symbolic AI over the years. I can only give you my own version of that. But I think my own version is fairly specific and fairly strong in its claims. I argued in this book that there were 3 minimal requirements. That a mind, I was mostly focused on human minds, but the same applies to AI, should really represent, excuse me, abstract relationships between variables, things that apply to all instances of a variable that you can freely generalize regardless of similarity. The second was a system of recursively structured representations like you would see in a tree structure in classical AI. And then the third was a distinction between individuals and kinds. And I argued back in 2001 that the neural networks that were popular then, we would call them multi-layer perceptrons, they're ancestors of current systems. I argued that they didn't do any of those things well. And I said it's not impossible to build a neural network that does these things, but to do it, you would have to recapture or recapitulate certain parts of symbolic AI. So neurosymbolic AI then would be a hybrid between classical symbolic AI and neural networks that would capture these 3 things, but also do some of the things we've come to know and love from neural networks, like learn over large quantities of data, maybe be able to do constant time inference in many cases, etc. One of the core arguments in the 2001 book was really about extrapolation and generalization beyond a distribution. The simple case that I gave then was if you took one of the multi-layer neural networks of that day and you trained it on the identity function for even numbers represented as sequences of binary digits, that's kind of the space in gray here, it would generalize some. It would generalize to other even numbers, but it wouldn't generalize to odd numbers or numbers that are larger than numbers it had seen before. And so I made a distinction between generalizing within a space of training examples and generalizing outside. And I said that neural networks that we know now in 2001 are pretty lousy at generalizing outside a space of training examples. And recently, Yoshua Bengio kind of started making the same point. This continues to be an issue, as I will show you. This eventually led others to more explicitly propose neurosymbolic cognitive reasoning. I think this is one of the classic books from around 2008. People have started to work on this. I would say it's still an unsolved field, but it's one that should get a great deal of attention. And I'll sort of put that in context. Ostensibly, everything has changed since my 2001 book, The Algebraic Mind. Back then, neural networks didn't do anything that was of practical interest. Nobody used them in production. They weren't even used in handwritten digit recognition at that, or maybe that's the one thing that we're doing is handwritten recognition, digit recognition, but that's about all they did. We didn't have GPU clusters. We didn't have an internet full of data of current internet size. Nobody was spending billions of dollars developing them. Most people had never even heard of neural networks back in 2001. I had to explain what they were. in order to even get the arguments off the ground. So now, neural networks do lots of practical things. We all use them every day in the background of many tasks. GPU clusters are everywhere. They're all trained on the whole internet, or most of it. Billions of dollars have been spent. Everybody has heard of them. So everything has changed. But I would argue that the reality is that all of the things that I was talking about, all of the problems that I pointed out then, remain problems and have not, in fact, been solved, despite all of the progress. So here's one example from a year or so ago. It's hard to do the following study correctly because usually the data is held tightly and the companies don't want you to know what they've trained on. But there are a few large language models like GPT-J where the training data itself is open. So you can ask a question. You can say, when you teach them something like multiplication, do they generalize that freely to new numbers? And it turns out they don't. They do better on numbers that they've been trained on than numbers that they aren't. Well, that's exactly the kind of phenomenon that I was emphasizing in the 2001 book. And in fact, as far as I know, nobody has yet built a large language model that can reliably multiply, say, 6-digit numbers times each other. My pocket calculator from 1970 could do that, or 1975 could do that. So there's some progress here, but this notion of abstracting something absolutely freely, philosophers might call it the intention rather than the extension, simply hasn't happened yet. We're still struggling. And you can see this all the time. One of the things I talked about in the 2001 book was operators. So plus or identity equals greater than. Here's an example from ChatGPT from not that long ago. There's a whole genre of examples like this on the internet, and performance is unreliable. Sometimes these systems get them right, sometimes wrong. Which weighs more, a kilogram of bricks or 2 kilograms of feathers? You get back what I would call fluent bullshit, 3 paragraphs with lots of interesting things that the average high school student wouldn't be able to tell what's what. And then in the final answer, it says, but in the air, 2 kilograms of feathers would weigh slightly less than a kilogram of bricks. That's failing to generalize, to freely generalize the notion of greater than, or less than, I guess, in this case. There are a million examples like this, too, where there's some abstract operation that the system seems to get the gist of, but it just doesn't get it correctly. So here on the left, somebody tried out Venn diagrams. On the right, I replicated the phenomena. You can ask these systems to draw Venn diagrams. They sort of get the flavor, but they obviously don't really know how to generalize the operation of what a Venn diagram should look like. So I tried Venn diagram with the words, I think, understanding, memorization, and prediction. And the problem that the deep Leppening problem that Greg Brockman laid clear remains. So that's actually a version of identity. It can't even retain the labels on the input to put them on the output of the Venn diagram. And then it just comes up with all kinds of incoherent nonsense. So that's another example where we still don't really have satisfactory abstraction, even in systems that have been trained on, essentially the entire internet. And this system might have cost $100 million to train. Here's another example from my friend Phil Lieben. He asked for infographics, and this would be, in some sense, though not entirely, a simple operation in a database. He said, draw maps of the United States where you illustrate each state with something that it's famous for. And it just makes stuff up. Like the one on the left has, 3 different versions of the Empire State Building distributed all across the United States in wrong places. The one on the right says that there's a city called New Angeles where they're famous for selling umbrellas, and it's in the northern, central part of the United States, etc. So again, you get something that sort of like approximates vaguely what you should get in an infographic, but clearly is not performing the operations correctly over the instances of data. And of course, the system has been trained on immense amounts of data. So it has lots of data to tell it where Los Angeles is and to tell it what Chicago might be famous for, and et cetera, and even what the names of the cities are. And it can't even keep that. Another example is bias. This actually also hinges in part on rules. So you would like to say, present your historical data in an accurate way, and maybe you want to, with your modern examples, represent diversity in some form. And we all know that Google screwed up on this massively last week. They probably did some testing, and I should make a point about engineering practice maybe. They probably did some testing to make sure that their effort at solving diversity problems that we already know exist in the systems work to some degree, but they didn't think to test it on history. And the system over applied things. So, for example, it reinvented who was on the Apollo 11. Lots of people made fun of them. Elon Musk went after them hard. Some congressman is already like calling for a congressional investigation of Google, blah, blah, blah. And really, what this shows you is that nobody actually knows how to make guardrails. You can argue about Google's politics all you want, but the point is nobody actually knows how to do this well. And I showed that by just taking another system, Bing, last week, just to show that the other bias also still exists in other systems. So I asked Bing to give me an ethnically diverse rock band on stage with 7 musicians. If you look closely, there's not 7 musicians there, but that's not my main point, the fact that these systems can't count, but they're all white males. So, it did not understand what ethnically diverse means. And in fact, we still have bias. So my joke about it is for every Google, there's still a Bing. Like Google was actually, although everybody's giving them a hard time, was trying to solve a genuine problem. And it's just a hard problem to fix given the current level of comprehension of the systems that we have. That brings me to compositionality and structured representations. So when DALL-E came out, I pointed out that it had trouble with examples like this: a red basketball with flowers on it in front of a blue one with a similar pattern. Anyone who's fluent in English and takes enough time can go through all 10 of these examples and discover that none of them are quite right. Some of you, probably many of you in this audience, will know what a bag of words model is. It's a little bit resembling a bag of words. It gets some red basketballs, it gets some blue basketballs, it gets some flowers, but it doesn't really know what goes where. I then, riffing off Steve Pinker's old example of man bites dog, as opposed to dog bites man, came up with an example in May of 2022 about trying to get one of these systems to do horse rides astronaut. And there were a bunch of lame excuses on the internet about how the system, has learned that horses are heavier than people and blah, blah, blah. The truth is you can actually get it to draw a horse riding an astronaut, but it's really hard because it doesn't really understand the structured representation, what the linguistics is telling it. Problem is not on the drawing side, but on the language and representational side. And then a week or so ago, for fun, I replicated this in a new system. I added a couple of distractor words because I know that the people who build these systems often address my specific examples by adding little patches and stuff like that. So I added in a bowl of cherries. And you still see this problem. A horse riding an astronaut that is sitting in a bowl of cherries, it just can't get it right. And, you can do prompt engineering for 20 minutes and find some way to do it, but it doesn't change from the basic point that it doesn't understand the compositional representation of the relations between the words of horse, riding, astronaut, etc. So, now we're talking again about models that cost hundreds of millions of dollars, which could, fund 10 academic research projects healthily for several years, and you're just not really making progress on this stuff. That takes me to type token distinction. So one of the central claims in the 2001 book was that you'd see a kind of bleed through that we would now call hallucinations. I think it was kind of one of the first anticipations of the hallucination problem. I gave an example. I said, suppose my Aunt Esther wins the lottery. This was in 2001. These kinds of neural networks that we had then would generalize that to other women or other women her age or other women living in Massachusetts, etc. It doesn't have a distinction between a property that is inherent to my Aunt Esther as an individual as opposed to the kinds that she belongs to. So we're still seeing that. That's really what hallucinations are about, is a failure of a proper type token distinction. For this crowd who thinks about ontology, it's obvious that you need such a distinction. It's axiomatic, but these systems don't really have that. They fake it by learning patterns representing relationships between language, but they don't really have underlying representations of individuals and kinds. So you get these weird kinds of things. Like somebody said, they sent me this on the internet. Please write me a 1-paragraph biography of GaryMarcus, mentioned his pet, blah, blah, blah. And it just made stuff up. So the first part of the biography was reasonable. You can call me a distinguished cognitive scientist, I don't mind. And an author, I clearly am, blah, blah, blah. All that's fine. But then it gets to notably some of Marcus's most piquant observations about the nature of intelligence were inspired by his pet chicken, Henrietta. Well, that's just garbage. I don't have a pet chicken. If I did, I wouldn't name it Henrietta. I do write about piquant observations about the nature of my children sometimes and what they tell us. So I have a New York Times op-ed, for example, about my daughter Chloe climbing through a chair. You can look it up. But I haven't written anything about my pets because I just haven't. And I don't have a pet chicken, so of course I can't write about pet chicken. So anyway, I showed this example at a conference in where was I, Munich, about 3 weeks ago, and somebody came back and sent me a really interesting thing, which is this. This is a children's book, Henrietta Gets a Nest by Gary Oswald. Well, I'm GaryMarcus, if you've forgotten my name. And what seems to have gone on is maybe just a kind of pastiching together of statistics of words, which is what these systems do. So there is a Gary who has written about a pet. It doesn't understand, the difference between GaryMarcus and Gary Oswald. It doesn't understand between writing about cognitive science and writing about pets. It's all just munged together. Another example I gave in my TED talk last year was Galactica saying that Elon Musk died in a car accident. Well, some people who own Teslas dying in car accidents, and he owns a fraction of Tesla, but that doesn't mean that he died in a car accident. And so it's again losing the details of individuals relative to the statistics of words. Okay. I'll skip this one. We don't need it. There is a big desire to believe that all these problems are solved. So somebody got really excited about Gemini, which is probably a billion dollar model that was just released, Gemini 1.5 Pro, and they fed in a Mr. Beast video, and they were wildly excited because it gave a summary of the Mr. Beast video. But all of these problems actually came out. The generalization and abstraction problem, the type token problem, the structured representation problem. It turns out that the summary was actually garbage. First one person posted, this is pretty cool, but having seen the video, it's not really very accurate. And then someone came up with a detailed thing. They found errors essentially in every paragraph. So like this notion that we're just going to solve it with more data is just never coming true. It's true that with more data, like they can do fun things they couldn't do before, like trying to summarize text, but it doesn't mean that it works. So I would say we still desperately need neurosymbolic AI. We're still facing the same problems with compositionality and so forth. We're actually incurring huge technical debt. Maybe I'll come back to that later. But at the same time, having told you that I think neurosymbolic AI is absolutely crucial to getting to a more trustworthy framework, there's some other things I think we need, which I think will be obvious to those of you in this audience who think about ontologies and so forth, but are really not part of the picture right now in the large language model tradition. One of those is explicit knowledge. I have an old slide here for fun. I showed this back in the GPT-2 era. I said that you should know that if you break a bottle that contains some liquid, some of the liquid will probably escape the bottle. And I said, look, we have general knowledge about bottles. And then I showed that GPT-2 did some ridiculous things, like it predicted if you break a glass bottle that holds toy soldiers, the toy soldiers will probably, instead of saying like, fall on the floor, will probably follow you in there. And so I wrote this slide and I said, without explicit manipulable knowledge, our models will remain uninterpretable and unreliable. So that was then. And now we say, well, what happened 2 years later? I don't know how many of you seen the video I'm about to show. I guess in a way my slides are not quite the way I want it. All right. So this is a really cool video on the subject of liquids and glass. See if you can figure out what's going on if you haven't seen it before. Right, that's ridiculous. Liquid actually comes through the glass jumps in the air and explodes, right? So we still have these kind of basic problems that we did back in I guess this was 2002. I have often talked about two kinds of knowledge that we need to think about critically. One of them is our kind of general purpose knowledge about the world, which is very broad. There can be expert knowledge, etc. And there's also what Spelke calls core knowledge. So I love this quote from her from, I guess it's almost 30 years ago now. If children are endowed innately with the abilities to perceive objects, persons, sets, and places, then they could use that perceptual experience to learn about the properties and behaviors of such entities. And then she argues if you don't have this firm basis, it's not clear how you can bootstrap in the world. And I think, in fact, that the experience that we've had with generative AI is the second part of our quote. It's what happens if you don't have core knowledge. Things get weird. And I'm going to give you some examples of things getting weird. I already gave you one with the glass. Here's two more. Watch this basketball. It's going to go through the hoop. Whoops. You get it to play? Yeah. So the basketball goes through the hoop. That's a violation. I'll pause here. Um, that's a violation of what Spelke likes to call the solidity constraint. Two things can't be in the same place at one time. And then she also talks about gravity, and we'll see a violation of gravity in the next video. But you can watch this again because it's fun to watch it explode. Obviously, a violation of physics. All right, now watch this. There's going to be a chair here underneath this paper, and watch what it does with gravity. Right? A child would think that's bizarre that it floats in the air, but Sora, I should have mentioned out loud, this is all from Sora, which is now $1 billion model also, and one that gets a lot of hype, does not understand gravity. But now, whoops, and pause here. You're going to see a guy in blue, and then next to him, this guy in tan. And I want you to watch what happens to him in terms of object permanence. Whoops, he just disappeared altogether, right? Basic physics, like there is no theory of physics on which objects just, instantly and spontaneously appear and disappear. So these kinds of things are still not represented in our AI. All right. And then I'm getting close to the end, and then I'll take questions. We also need reasoning and cognitive models. In the article I mentioned, I'll show you in a second, next decade, in AI, I separated reasoning and cognitive models into two separate pieces. There's a rumor that neural networks of the current variety reason. There's great empirical work by Melanie Mitchell in Archive a month ago that I don't have on the slide yet, showing that if you control for content so that you're not just looking at memorized examples and familiar materials and so forth, the reasoning is really very limited. And similarly, I don't think that the kinds of systems I just showed you have cognitive models over time. So for example, the last video does not know the system doesn't know how many people are there, and that's why it's free to simply have one disappear from 1 minute to the next. It lives in the space of pixels and frames and sequences of frames, but doesn't have an abstract representation of the individuals and entities that are there. There's only like 15 videos I know of Sora, but if you look at those 15 videos, at least half of them, you see weirdness like that. You see either violations of gravity or object permanence, things coming and going, etc. We need to have systems that can actually reason about the entities that are in some scene or some environment, some situation. We need to have not just abstract knowledge about the world over time, but representations, let's say, in the context of reading a story or being in a situation and so forth, knowledge pertaining to the relationships between entities there. Again, I would say the neural network tradition is falling short. I see neurosymbolic AI as a prerequisite to being able to do these things, but nobody really has a good system yet. Here's the article, Next Decade in AI, and also a mention of my 2019 book that some of this draws from with Ernie Davis, Rebooting AI. So I will summarize. I just have 3 more slides, and then I'll take questions. The first is, I think we can put the idea of scaling is all you need to bed. Scaling alone is not all you need. That doesn't mean that there's no value in scaling. The law of large numbers has always told us you get a more accurate answer if you have more data. But that's not enough. Current deep learning still struggles with reasoning and factuality, even given vast amounts of data and enormous models. Classical AI alone is not the answer either. We have to combine learning, which so far the deep learning tradition does better, with abstraction. Neurosymbolic approaches, I think, offer some hope there. But advances in neurosymbolic AI alone are not going to be enough. Quite simply, intelligence is multifaceted, and we should not expect a one-size-fits-all approach to work. We're also going to need large-scale knowledge, including some innate nucleus geared around things like causality, basics like agents, sets, and places, just like Liz Spelke said 30 years ago. We're going to need rich cognitive models. We're also going to need advances in engineering methodology. The truth is, nobody knows how to build robust cognition at scale. You can think about our experience with driverless cars in this regard. Some people have tried pure rule-based approaches. Some people have tried pure deep learning approaches. Everybody winds up playing whack-a-mole. Everybody winds up like fixing one problem, causing another problem. Nobody has a systematic way to do this, which is why driverless cars, it's 12 years since Sergey Brin said we'd have them in 2017. They're still not here. They're not even close. Probably the closest effort is Waymo, and they only work in cities that are extremely well mapped with very good weather and limited numbers of pedestrians. There's no hope, I think, of taking a Waymo and sticking it in Boston or Mumbai and having it work out of the gate. This was not going to happen. Right. In Mumbai, you have different traffic patterns, you have different vehicles. In Boston, you have snow. Like, there's no serious argument that we're anywhere near that. Okay. So we need to learn how to build complex cognitive systems. So far with large language models, it's a lot like an old XKCD cartoon about machine learning. I don't know how many of you have seen the cartoon. There's somebody standing in front of a big pile of dirt. And somebody says, that's your model, this big pile of linear algebra? And the other person says, yeah. And they say, well, what if it doesn't work? And they say, well, you just stir the pile. And basically that's what's been happening, except we have one bonus feature since that cartoon came out, which is we now know how to make bigger, bigger piles. But that's it. That's what we have in large language models, is you get bigger piles of data and you stir and you hope for the best. That's not a serious engineering methodology. And what we're seeing is technical debt. People build these systems and then they suddenly break. Like OpenAI had a total meltdown last week. Nobody really knows why. And if you think that's an isolated incident, I'm here to tell you that Google had the same thing yesterday. So we really don't have a good handle on how these systems work. So bottom line, looking for a quick win is distracting us from the hard work that we really need to do. And the last thing is, I'll go back to 2021. Ernie Davis and I wrote this paper criticizing the foundation model approach. And we made 7 suggestions then. We said that to succeed, and this was basically from our 2019 book, you'd need rich cognitive models that keep track of the dynamically changing world. I hope I've persuaded you that Sora does not have that. We said you'd need extensive real world knowledge, like you need to know that most people in Warsaw speak Polish. I would say we actually have made an advance there, that large language models are helpful there. People like David Ferrucci, who work in a neurosymbolic tradition, are able to extract some knowledge from the large language models. So we made progress on that one. Representations of relationships between entities. I think we're actually still pretty weak on that, as the horse rides astronauts examples show. We talked about compositionality. Again, the horse rides astronaut examples show we have not solved that problem. We talked about common sense knowledge, including time and space and causality. Sora shows you that we're still working on that. Reasoning, I think Melanie Mitchell's recent work is probably the best. I should have that in this deck, that's an archive in the last month or two. We're still miles away from being able to do that well. And one thing I should have mentioned is human value. So for example, a medical advice chatbot should not recommend suicide. Somebody just gave me an example. It was admittedly a jailbreak, but it was very simple jailbreak. They put an emoticon in a conversation that they had with, I think it was ChatGPT a couple days ago, discussed suicide. It was not hard to get ChatGPT to say something like, you shouldn't commit suicide, or maybe you should. So we still have systems that don't have the ability, or that lack the ability to represent even the most basic ethical principles, like don't tell people to kill themselves. So I think we're still a very long way from a solid foundation for AI. I don't think we can get there except to go through neurosymbolic AI, through ontology, and through better reasoning. I thank you.